Hi, everyone. Thank you for taking the time to view the longer version of the conference talk on small box cryptography. This is joint work with Yevgeniy Dodis and Daniel Wichs. What is the biggest open problem in cryptography? There are several worthy candidates, and there's definitely no right answer, but one candidate that we feel should be of commendable interest is the provable security of AES. The simple reason is that it's used every day and everywhere. So given its ubiquitous usage, let's look at what is AES. Well, if you write down AES in its full glory, it looks a bit messy. But we theoreticians love a good abstraction, and we have done just that by abstracting AES away into something called as a substitution permutation network. So SPN, in short, is basically a sequence of structured rounds where you have three steps: a key addition step, a substitution step, and a permutation step. And the only piece in this puzzle that is non-linear and also the source of hardness is the S box. And also AES inspired as a whole legion of popular ciphers which follow the same design. Which brings us to the question, can we prove security? Unfortunately, we cannot, at least not unconditionally, without proving P versus NP. But there are some results under some restricted type of attacks. But we want to be ambitious. Can we prove it secure in some idealized model or assumption? Unfortunately, we hit a roadblock because it's unclear how to model this S box, because that is the only source of hardness. And it is also very small by design because you need AES to be efficient. And also there is no sound theory on hardness that we can achieve by iterating something that's so small or simple, like an S box, over multiple rounds, or at least that was the case until this work. Which brings us to small box cryptography, and I'm going to tell you this right now. So it is a mixture of proofs and hardness conjectures. The former is something we like, and the latter is something that we need unless we solve P versus NP and take home $1 million. It consists of three steps, which we can apply to a lot of the primitives, including, and we do it for the SPNS setting, and also PRG, or a stream cipher. The first step is basically a traditional reduced round proof. And the second step is a hardness amplification, which could be possibly provable. And in the case of SPN, it is provable if you know the key schedule. The third step is the conjecture part of the puzzle, which is called the big to small conjecture, which essentially is the one-way function equivalent of this new branch of crypto called small box crypto. And the biggest gain from this is that everything is specified. It explains existing results and hopefully will guide new designs. And we also derive precise quantitative bounds with explicit dependence on number of rounds. And what we achieve is something that's strong, but definitely more conservative than actually the real world choices. Which brings us to the case study of SPN. So what is our result? So when we use the most aggressive big to small conjecture, we get the following bounds. Sorry, the rounds and bounds are definitely tongue twister here. We get epsilon is equal to 2 to the negative 8R over 3 security in R rounds, which is actually pretty respectable. We get 1 over 100 million security for 10 rounds, which is what AES does, and pretty much 2 to the negative 64, which is excellent in 24 rounds of security. And all of this is for a random S box. And this works with any linear P box, subject to the small caveat, as long as the inverse has no zeros. So what we get is an almost real AES. And we believe this is good because it guides future designs and it's quantitative, and everything is pretty neatly specified. There is no uncertainty. So let's look at contrasting small box crypto with a traditional crypto, which we call big box. So big box crypto has this box or a hard object, which is at least security parameter big. So we typically have these assumptions or these idealized models using a random oracle, ideal cipher, random permutation, generic group, so on and so forth. The big issue is that it does not capture the real world symmetric crypto because the abstraction that happens when we use these big boxes is too coarse, so that some of the most interesting parts, like an S box, you lose the entire quality there. And when we actually have very small rounds, we actually don't get any quantitative bounds that's meaningful from traditional crypto. So what does traditional crypto do when analyzing SPN? Well, it simply replaces the entire substitution permutation structure with a big permutation pi. But the problem is that we really can't call it a substitution permutation because there's no substitution happening. So we call it key alternating cipher. Now the security is proved in we prove the security in the random permutation model, which is the big box equivalent. But what we get is that even one round is secure, the famous Ivan Mansur cipher. But the question remains, is it enough actually to bring practice to theory? And the answer is that it does not appear to be sufficient. So what are the problems with the big box? We abstract away the SPN structure, which is sort of the heart of the design, and with this big box of a permutation, and we lose the structure. And it's quite difficult to implement these big random permutation. And most existing candidates are never ideal. So we need this ideal functionality from this random permutation, but the SPN, for example, is never ideal. And why is SPN better than any other permutation? So what guides the choice of the permutation is also a big question. And the proof guarantee sort of vanish when we look at any concrete implementation. And the predicate number of rounds is actually too low. So we know that no one round SPN is secure. And in fact, it has been shown by a sequence of works that the exact security of key alternating cipher increases with the number of rounds. But all of this work is again in the random permutation model where we use monolithic random permutation. So there's again some kind of a disconnect. But the main thing is that there are no meaningful, at least quantitative bounds for exact security dependent on the number of rounds with real SPNs, which was actually implemented. So what is our selling point? How do we sell this to the practitioners? We have an SPN, and we have 2 to the negative 8R/3 security in our bounds. We will, in our rounds, we will derive that in just a few slides, which I think would delight practitioners. On the other hand, something with is used in the big box, it's a whole bunch of question marks in the security. We don't know what's the security. That's a function of the number of rounds, and we don't know how to implement or what is a good permutation pi, which would leave the practitioners scratching their heads. So now let's open up the small box and figure out how we actually derive the 2 to the negative 8R/3 bound. As we saw before, small box cryptography is a mixture of proofs and hardness conjectures. It's 3 steps. So let's tackle the first step, which is done in the big box world. And it's also called as domain extension. So how do we do this? These are the parameters for an SPN. We ignore the actual values for AES, and we model the S box as a publicly available random permutation because it is also the only source of hardness. And the best possible security would be something like 2 to the negative n. Clearly, when n is equal to 8, this does not make sense, but we will think n is at least security parameter for now. So the traditional hardness questions that we have asked is, what is the minimal number of rounds R for SPN security? To this end, we will use the results of Karthikeyan et al., where they've shown that any three-round linear SPN has a security which is O of W, which is big O of W squared, Q squared by 2 to the n. And we will use this result and combine this with the step number 2, which is the hardness amplification step, which is also again done in the big box world. And the idea here is that if I take the same thing and run it repeatedly for multiple rounds, we amplify the security. And this could be unconditional with independent keys as shown by Maurer et al. But what is it in the context of SPN? The ideal hardness amplification, the dream result is basically to say that if I can break one instance in T comma epsilon hardness, then I can break C such independent instance, the keyword being independent, in the same time T and epsilon to the C. But it has been shown that in its full generality, this dream hardness amplification result is likely to be false. But it seems true for most practical instantiations, and it's probably true in many information theoretic settings, including the cascading of block ciphers, as shown by Maurer et al., when we assume independent keys. So what do we mean by a cascade of an SPN? So when we have a cipher E1, E2, and we want to cascade it, we basically apply the output of E1 as an input to E2. So we can also do the same thing for the same cipher E, where we do C cascading, where we cascade E itself C times. And this requires the keys to be independent in theory, but in practice, we have something known as a key schedule. So what does the Maurer et al. Work give us? It gives us that if I have Q comma epsilon security of E cascaded C times is Q comma 2 epsilon, whole thing raised to the C secure. So now when we apply it to a three round linear SPN, we get 3C round linear SPN, which is Q comma Q squared over 2 to the n, everything raised to the C security. Now this is unconditional with independent keys, and otherwise we can only conjecture it. So what we achieve is an amplified security for the same running time of the adversary that's mounting an attack. But know that all of this is still only meaningful in the big box world. Now we have done the first two steps, which brings us to the magic ingredient of big to small conjecture. And obviously, because it being a conjecture, it definitely needs further study. But before we go into this big to small conjecture, it makes sense to prepare for magic. Magic cannot happen immediately, at least not in the cryptography world, so we need to prepare it. So what we do is we replace the number of queries Q by running time T. So this is the time that we want the attacker to be upper bounded by. So we get 3C round linear SPN is T comma T squared over 2 to the n, everything goes to the C security. Now I want fix T to be the value that we want at the end. So just for us to remember that nothing changes. But note that the epsilon value that you see here is actually dependent on T. And that is a problem for us. So we will remove the dependence of T in the security epsilon by placing explicit lower bound on the size n. So what we will say is that, well, if n is greater than 20 log T, then we get that the any 3C round linear SPN is 2 to the negative 0.9 Cn secure. And what we get is a new security definition, T comma 2 to the negative 0.9 n to the C secure. And when we put R is equal to 3C, which is the number of rounds we get, R round SPN is T comma 2 to the negative 0.3 Rn secure, provided n is greater than 20 log T. Now with this done, let's move on to the conjecture part of the puzzle. So how do we go from the big to small conjecture? So this is what we have. We just proved it. Any R round linear SPN is 2 to the negative 0.3 Rn secure, provided n is greater than 20 log 8. But what we really want is R round security if n is equal to 8. So when we plug in n is equal to 8 here, we get T comma 5.28 to the negative R secure. But there is a discrepancy. We have n is equal to 8 and n is greater than 20 log T. Clearly, both of these cannot be the same. But let's just assume it. That's the conjecture part of the puzzle, because we need some crazy assumption anyway. And this is essentially big to small conjecture. But we need to be a bit careful because there can be brute force attacks, because when I reduced n, I have smaller key length, and when we use key schedule, there could be some brute force attacks, but I'll refer you to the paper for details because it's not really a big deal in practice. So what is the philosophy? Big to small philosophy. We have a natural construction that makes sense for any n. So we get t comma epsilon of n security, but only if n is greater than a log t in the that's what we get. And clearly the proof breaks down if n is too small. But then we don't have any matching attack except there could be brute force. So we want epsilon of n to be meaningful and still great, even for n is equal to constant, which is what we achieve because even though the proof breaks down, there is no matching attack. So the big to small conjecture heuristic is this. Now, yes, supporting proof will break down when we have n just be a constant, but we still get t comma epsilon prime of n security for epsilon prime of n approximately equal to epsilon of n, even for n greater than constant. That is the heuristic part of it. So now we get a whole lot of options based on what is the definition of approximately, what is the definition of a constant, etc. But the most aggressive version of epsilon prime of n would be something like epsilon prime of n is equal to epsilon of n plus the security loss that we get if we allow a brute force attack to happen within time t. So this is the security. So clearly there could be constructions where there is a brute force attack that just renders the whole thing invalid. And therefore this epsilon prime of n that we have computed will account for this brute force attack. So the question is this good? Is this philosophy good? Well, the hope is yes, but again, we need to be careful because it's clearly false when we have direct product operation in place of a cascade. So say I want to invert s of x1 dot 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 x of r, when we know that this is t comma 2 to the negative rn over 2 hard if n is much, much bigger than log t. But it trivially breaks down if I have n is equal to constant because I can bound a brute force attack. But then there is no known attack for something like cascade or an XOR, where the operation sort of destroys the individual instances, right? So general attack on cascade might also attack AES. So we want to design, we also design a stream cipher in small box crypto framework under a variant of LPN. There's nothing behind the scenes. But clearly, we need more validation because we have demonstrated a possible collision between the big box and small box world, but we clearly need more validation. So let's look at how a stream cipher or a PRG meets small box cryptography. What we have is a function f, which produces just a bit. It's a trivial PRG, especially when we assume f is a big random oracle, even though it's non-expanding. So let's make it interesting for us. Let's make it expanding. So this is what we mean by domain extension. So where we extend the output domain, also known as the range, I know, to 0, 1 to the L with the following construction. G of x is f of x concatenated with 0 is f of x comma 0, f of x comma 1, and f of x comma L minus 1, all concatenated together. The step 2 is hardness amplification. We know that the XOR operation is fine, is the standard thing for a PRG. It's proven secure in the information theoretic setting by Maurer et al. And in the computational setting by Dodis et al., which gives us the following construction, where I have C inputs, x1 through xc. I apply f of x1 comma 0, XOR it with f of x2 comma 0, so on and so forth, f of xc comma 0. So this is my first bit. This is my first bit, and then I do it for each of the L minus 1 remaining bits. So we, at the end of the day, we get L bit output. And this is the following construction. So now let's analyze this. And we can do this in one go, fortunately, in the idealized big box world, when we assume f is a random oracle. So what we get is G tilde is t comma t over n raised to the c secure when n is 2 to the n, when capital N is 2 to the small n, and t is the number of queries to f. So when we have n is greater than or equal to 10 log t, this is the magic preparation step. We have t comma n to the negative 0.9 c security. So now we have the big to small conjecture, where this epsilon prime of t is now introduced to account for the brute force search that can happen in time t. Okay, but the construction that we saw before, we can also analyze it in the big box world, where we can independently from big box, we get a secure length doubling PRG under the exact LPN assumption. So we have demonstrated a collision. We have used our recipe of domain extension, hardness amplification to construct a candidate PRG. We have, and we can prove it to be secure in the big box analysis with nothing, no conjecture, no magic happening. It's plain and simple. And we also have it analyzed in the small box world. Which brings us to the question, why is all of this relevant? Why is this better than just saying, AES is secure and moving on? Well, we use a fair bit of proof, and it's quite involved and technically non-trivial. And we get bounds in a systematic way. There's nothing hand-wavy. The only part is big to small conjecture. But again, the conjecture is actually quite syntactically natural. And we definitely want people to either break or validate it. And that is what we invite the practitioners to do, because on theoreticians to prove one way or the other theoretically and look at big to small conjecture with a little more, with a little bit of a magnifying glass. Well, let's look at the big picture, right? So what we have, we need theory of hardness for some small components like an S-box, and the conventional models or assumption fail. So the only thing we can do is something like the big to small conjecture, which is a new type of assumption friendly to small box cryptography. We think it's the equivalent of one-way function of big box cryptography. And we introduce a new philosophy for design and analysis. What we do is we go to the big box world. We have no way to do anything in the small box. That's big box has a lot of tools, and we want to go there. We do everything that we can prove there, and then we come back to the small box. But we come back with the proofs and techniques that we have in the big box world. So it's not a simple empty journey into the big box. We come back with something. But clearly a lot of work remains, looking at Feistel ciphers, looking at the big to small conjecture itself. But we hope that this starts off a new paradigm of cryptography, and hopefully it's exciting enough to sort of bring more of practice into theory. And we'll see you in the real world, or well, in the Zoom meeting when I'll be giving a short abridged version of this talk, and I'll take questions. Thank you.